Hello and welcome back to the channel. Today we're going to be reviewing a slightly more complex version of the question that appeared in the previous video, the link to which will be in the description below. So as you can see, now in our diagram we have what are known as mass fractions, which indicate the composition by mass of each species in each stream. Here we have what is called a binary system, where we have just the two species, denoted by species 1 and 2, where the notation implies that this is the composition of species 1 in stream 1. So the number before the comma is the stream number, and the number after indicates the species. So notice these units here of kilograms per kilogram, which are fairly essential where in applications you may end up with mole flow rates, volumetric flow rates, and in order to denote what unit their composition is given in, it is paramount to indicate whether it is on a mass basis, a mole basis, or a volume basis. In this case, everything's rather simple, all in mass flow rates and mass compositions. Notice how, because it's a binary system, in all of our streams, our mass fractions sum to 1. So for stream 1, 0.7 plus 0.3 is 1. Stream 2, 0.9 plus 0.1 is 1. And stream 3, 0.1 plus 0.9 is 1. These numbers here do not have to be, so for example, where the composition of species 1 in stream 2 is 0.9, it doesn't mean it has to be 0.1 here. These numbers have just been selected for ease of calculation during the solution phase. So in the previous video, we alluded to something that's known as a degree of freedom analysis, which is a very important technique indeed. So this is going to be the first time that we perform explicitly a degree of freedom analysis. And the best way to do this is for a system like this is to do it stream by stream. So we're going to start off evaluating our unknowns, starting with stream 1. So for stream 1, we have the total mass flow rate, and we have explicitly both intensive variables for the compositions. So for stream 1, we have no unknowns. For stream 2, we have both intensive variables denoting the composition on a mass basis. However, we do not have the vital extensive variable M2. So for stream 2, we have one unknown, which is M2, where M2 denotes our mass flow rate of stream 2, total mass flow rate of the stream. For stream 3, we have exactly the same as stream 2. We have both of our intensive variables, 0.1, 0.9, where it's important to note for a binary system, if you are given just one of the mass fractions, the other one is technically given, as if you know this is 0.1, knowing the fact that mass fractions must sum to 1, you know this has to be 0.9. But again, we do not have the vital extensive variable, so we again have one unknown, which is M3. So in total, from all three streams, we have two unknowns, M2 and M3. Now the second part of our degree of freedom analysis is to write down how many equations we have. Well, in a chemical engineering process where you have n species, so here we have 2 species, but for n species within the process means we can write n mass balances. So in our case, for the binary system, n equals 2, species 1 and 2. So that implies we have 2 equations. As we will go on to in the solution phase of this video, these 2 equations, they can be the mass balances on species 1 and species 2, or it can be the total mass balance, so 100 equals M2 plus M3 and one of our component balances. You can't write all 3 because then the equations will not be independent, and you'll have 3 equations for only 2 unknowns, so you'll have a negative number of degree of freedom. So now, finally, now that we know our unknowns and our equations, again, 2 unknowns and 2 equations, let us calculate and confirm we have 0 degrees of freedom. So our number of degrees of freedom, end off if you will, is the number of unknowns, 2, minus the number of equations, 2, which is indeed, at least hopefully, 0. So that means a degree of freedom of 0 means that we have a unique solution, or a unique solution is possible. If the number of degrees of freedom is bigger than 0, it means that you can solve it. It's just that technically you'll have infinitely many solutions. There will not be this desired unique solution. So now that we've done our degree of freedom analysis, we can now move on to writing our material balances. So having verified we have 0 degrees of freedom and recalling what we said earlier about being able to write 2 material balances, for the ease of calculation, I'd recommend here to write the total material balance as one of your equations, and the second equation being a material balance for one of the components. Okay, so here we go. How do we solve this problem? Well, the solution, our first equation, as you may have guessed, is going to be our total material balance. So that is going to be what comes in, which is our 100 kilograms per hour in. I remember from our previous video, here we're assuming that there's no reaction. So in our material balance, our consumption and generation terms are both 0. And we're also making that assumption of steady state conditions, which means accumulation is 0. So all of our material balances, recalling from the previous video, in minus out plus gen minus consumption equals accumulation. Well, all of these terms down here are 0. So all of our balances will be in the form in equals out. So in comes 100 kilograms per hour and out goes M2 plus M3. In is 100, out goes M2 and out goes M3. So our second equation that we're going to write is going to be our component balance on species 1. So anything where it's comma 1, stream 1, comma 1, 2, comma 1, 3, comma 1. Those are the mass fractions we're using. The viewer is advised to pause here and potentially try, after watching the solution here, go back and try writing the corresponding material balance for species 2 and see if you can reach the same solution as we reach. So for species 2, in comes 100 kilograms per hour. And this is where we need the composition multiplied by our mass fraction of 0.7 kilograms per kilogram. And notice how the units will yield kilograms per hour on this side. And that's going to be equal to 0.9 kilograms per kilogram times by M2. So we get 0.9 M2 kilograms per hour plus 0.1 M3. And the opposite is you'd use the other numbers if you're trying to balance using component 2. So that means that the second equation yields that 70 is 0.9 M2 plus 0.1 M3. Now from mathematics, you'll know that when solving simultaneous equations especially, the number of unknowns must be equal to the number of equations. And again, to verify the findings from our degree of freedom analysis here, we have 2 equations with 2 unknowns, M2 and M3. M2 and M3. So if we call this tidied up one, equation 3, what we're going to do is substitute equation 1 into equation 3. So we're going to replace M3. So what we'll get is that 70 is equal to 0.9 M2 plus 0.1 times by rearranging equation 1 for M3 is going to give us M3 equals 100 minus M2. So 100 minus M2. Neatening this up, we'll get that 70 equals 0.9 M2 plus 10 minus 0.1 M2. Again, further simplifying, we'll subtract 10 from both sides. 60 equals 0.9 minus 0.1, so that's 0.8 M2, which means that M2 is equal to 60 over 0.8, and then 60 divided by 0.8, which is 75 kilograms per hour. And now, using what we have here, which is 100 is M2 plus M3, well, if M2 is 25, therefore M3 is input 100 kilograms per hour minus 75 kilograms per hour equals 25 kilograms per hour. So therefore we've solved the problem and found that our unique solution for our 0 degrees of freedom is M2 is 75 kilograms per hour and M3 is 25 kilograms per hour. It's always important to state the unit. And there we go. And you can easily verify that. If you wanted to check the answer further, substitute back into equation 2 and that should hold true. But obviously from equation 1, our total mass balance, 100 in, 75 plus 25 out, our mass is indeed conserved. Thanks for watching, and I'll see you in the next video.